Welcome to the deep dive. We're the show that gives you that shortcut, that essential download on the topics shaping our world. And today we are plunging right into artificial intelligence.
Yeah, AI. It's absolutely everywhere, isn't it? From, the phone in your pocket to these massive headlines. But it's often wrapped up in so much hype, so much mystery.
Exactly. So what is it really? How does it actually work under the hood? And maybe most importantly, what does it all mean for us now and, down the road?
It's a huge field.
Yeah.
Credible promise, definitely, but also some pretty significant challenges, too.
Right. So our mission here is to cut through that noise, go beyond the easy headlines, the sensational stuff. We want to explore the foundations, the big breakthroughs, and maybe the tougher questions AI makes us ask.
And we're doing that by digging into a whole stack of sources, pulling out the key insights for you.
That's the plan. So today we're going to unpack how AI evolved. Look at the different flavors of AI, how it learns to, find patterns in all this complex data.
And how those abilities are changing things, changing industries, changing our lives, and raising some really critical questions along the way.
So get ready. Let's explore it, question it, and hopefully really understand it. Part 1. AI's genesis. From early ideas to foundational paradigms. Okay, first things first. Let's try and cut through some of this AI hype. Because honestly, sometimes the term AI itself feels a bit like, well...
Like snake oil.
Yeah.
It gets thrown around so much it almost loses its meaning, doesn't it?
It really does. So we need to build up some vocabulary here, figure out how to tell the different types of AI apart, and how to look at these new claims with a more critical eye.
That's crucial. And our sources start right there, teasing apart these classifications.
Yeah.
You've got, say, generative AI. That's the stuff creating new things, text, images, music, writing stories, making digital art.
Right, like ChatGPT and image generators.
Exactly. And then on the other hand, you have predictive AI. This is about forecasting what might happen based on past data, predicting stock prices maybe, or disease risks, or what people might buy.
Okay, two different goals there, creating versus forecasting.
Very different. And actually, some of our sources make a really strong point here that predictive AI, especially for really complex things like human behavior, it might likely never work accurately.
Really? Never work. Why?
Well, think about it. Human behavior is just so messy, right? So many variables, it's nonlinear, people are unpredictable. Trying to reliably predict that, it's maybe an almost impossible task. The inherent difficulties are just immense.
That's a sobering thought. So why is making these distinctions generative versus predictive, for instance? Why is that so important?
Because the way it's often reported, the news media can sometimes mislead people. Maybe not intentionally, but
How so?
they often focus on the flashiest results, without really explaining the tech behind it or its limits or even what it's really being used for. And that just creates confusion. It makes it hard for anyone to know what's a real breakthrough and what's just noise.
Yeah, I see that. Our sources mention how reports often uncritically repeat PR statements, use too many pictures of robots.
Right. And they talk about AI like it has agency, like it wants things while downplaying the real limitations. It feeds this hype cycle.
Which obscures what's actually happening.
Absolutely.
Yeah.
And it circles back to needing that fundamental skepticism. This constant talk about the bugbear of existential risk, AI taking over the world someday.
It's sci-fi stuff.
Yeah. Sometimes that distracts from the more immediate harms of AI snake oil, as one source puts it. Things like bias in algorithms, deepfakes, spreading misinformation. These are happening now.
These aren't future problems, they're current issues.
Exactly. Tangible impacts. So being able to tell the difference between real progress and hype, knowing what kind of AI we're talking about, that's just essential for navigating all this.
Okay. So with that critical lens firmly in place, let's rewind a bit. Back to the early days of AI research. Because it wasn't always about chatbots and image generators, was it? The field took a pretty major turn early on.
Oh, yeah, a significant shift. It's fascinating, actually. You had these two sort of parallel paths, two very different ideas about how to build intelligence.
What were they?
On one side, you had the early neural networks. Think of them as trying to mimic the brain, very loosely, with simple connected neurons processing numbers. They learned by finding statistical patterns in data.
Like learning shapes by seeing lots of examples.
Kind of, yeah. But back then, the computers just weren't powerful enough, and they didn't fully understand the best way to structure these networks. They were nowhere near as capable as fully connected networks would have been with today's tech. Conceptually cool, but practically limited.
Okay, so neural nets were interesting but hit a wall.
Pretty much.
Yeah.
Because of those limitations, interest really faded in the 1970s. People talk about an AI winter for that approach. And the research community's attention swung pretty decisively over to symbolic systems.
Symbolic systems, what does that mean? How were they different?
Totally different approach. Instead of numbers and stats, they worked with discrete symbols, categories, concepts, and they had rules, explicit logical rules programmed right into them.
So less like a brain learning, more like a very detailed instruction manual.
Exactly. Or a super complex flowchart. The classic example is an old chess-playing computer. It didn't learn statistically from games. It examined billions of possibilities of the form. If I play X, my opponent might play Y, and then I could play Z, and I would be winning.
Pure logic and calculation based on programmed rules.
Precisely. Logical deduction, searching through possibilities defined by rules. A complete contrast to how neural networks learn from data. And this symbolic approach, it was powerful in its own way, very logical, a bit rigid. It really dominated AI research for decades.
Part 2. The deep learning revolution, finding patterns in data. Okay, so fast forward a few decades. Symbolic systems had their time, neural networks were kind of in the background, and then boom, neural networks make this huge comeback.
A massive comeback. And it was mostly thanks to what we now call deep learning.
Deep learning, that's the term we hear all the time now. What was the actual breakthrough? What made them go from, unusable to usable for many domains? What changed?
A few things came together, but a big part was the architecture itself. These deep, layered structures. Think of it like processing information in stages. Each layer learns increasingly abstract features from the layer below it.
Building complexity layer by layer.
Right, but just having layers wasn't quite enough. The real key, the technique that made them trainable, was backpropagation.
Backpropagation. Okay, unpack that for us.
It's basically an efficient way to train the network. Imagine the network makes a guess, say, trying to identify an image.
Yeah.
If it gets it wrong, backpropagation is the algorithm that goes back through all those layers.
Tracing the error back.
Exactly. And it figures out how much each connection, each synaptic strength or weight between neurons contributed to that error. Then it adjusts those weights just slightly to do better next time.
Like tuning an instrument based on the sound.
That's a great analogy. It's this iterative process of predict, check, error, adjust weights, repeat, and it allowed these deep networks to actually learn complex things effectively.
This is where it gets really interesting for me. Take something like recognizing a cat. How does a machine learn catness? You can't just program rules like pointy ears, 4 legs, whiskers, because cats look so different.
Right. That's the beauty of it. Deep learning doesn't rely on explicit rules like that. During training, it's mathematically designed to maximize what's called an objective function.
An objective function, like its goal.
Precisely. In cat recognition, the objective is simple. Maximize the probability of correctly saying cat when it sees a cat and no cat when it doesn't. It's all about optimizing for that goal through trial and error.
Adjusting those internal weights we talked about.
Exactly. It keeps tweaking its internal parameters until it gets really good at that specific task. And once it's trained, that network becomes essentially a giant mathematical equation that performs inference on new images. It sees a new picture and calculates the probability, cat or no cat.
And this worked much better than previous methods.
Dramatically better. Our sources talk about the dramatic reduction of image recognition errors before and after deep learning was applied. It wasn't just a small improvement, it was transformative.
Wow. It really shifted image recognition from something error-prone to something incredibly useful. You see it everywhere now, phone cameras, medical scans.
Absolutely. It turned a theoretical possibility into a practical reality.
Okay, so that's how they learn with label-supervised learning. But you mentioned AI could also find patterns without labels. How does it cluster information or map complex input spaces all on its own? Finding structure in chaos, basically. How does that work?
Now we're getting into unsupervised learning. This is where the AI isn't given the right answers beforehand. It just gets a big pile of data and has to figure out the hidden structures itself.
Like sorting laundry without knowing what the pairs are?
Kind of, yeah. And there are different ways it does this. One common technique is k-means clustering.
K-means.
So imagine you have a cloud of data points. K-means tries to divide them into k distinct groups, or clusters. You decide how many clusters k you want beforehand.
Right.
The algorithm's goal is to minimize the distance between each data point and the center of its assigned cluster, the centroid. It does this iteratively. First, assign each point to the nearest centroid, that's the E step.
Expectation.
Right. Then recalculate where the center of each cluster should be based on the points now assigned to it. That's the M step.
Emphasization.
Exactly. Assign, recalculate, assign, recalculate. It keeps doing that until the clusters stabilize, until points stop switching clusters. It finds those natural groupings in the data automatically.
Sorting the socks into piles based on similarity.
Pretty much. Another powerful method, slightly different, is Gaussian mixture models, or GMMs.
Okay, GMMs, how do they differ?
Instead of hard boundaries like k-means, you're in cluster A, you're in cluster B, GMMs are probabilistic. They assume your data is generated from a mix of several underlying bell curve Gaussian distributions.
Like different ingredients in a smoothie contributing to the overall taste.
That's a good way to think about it. Each data point has a probability of belonging to each of the underlying Gaussian components. It models the data's density as this weighted mix.
More nuanced than just assigning to one cluster.
Yes. But there's a catch. A challenge with GMMs is avoiding singularities. That's where one of those Gaussian components might sort of collapse onto a single data point, becoming infinitely narrow and tall.
Which sounds like overfitting learning the training data to perfectly.
Exactly. It means the model isn't generalizing well. So you need techniques to prevent that collapse, to make sure the model captures the real underlying structure, not just noise.
So these methods, k-means, GMMs, they let the AI sort and group data, finding commonalities without being told what to look for, like finding constellations without a star chart.
Precisely. And this whole area of unsupervised learning, finding structure automatically, was a huge step. And this brings us to someone really important here, Teuvo Kohonen. Yes, he developed something called self-organizing maps, or SOMs. This was another key unsupervised learning technique.
Self-organizing maps, what was special about them?
Unlike just clustering, SOMs aim to create a map, usually a 2D grid, that represented the relationships in high-dimensional data. Imagine taking, I don't know, thousands of different animal descriptions and arranging them on a grid so that similar animals end up close to each other. Lions near tigers, robins near sparrows. That's what an SOM tries to do.
How? How does it organize itself?
It uses competitive learning. Neurons on the map compete to win an input data point. The winning neuron and its neighbors on the map that adjust themselves slightly to become more like that input.
So similar inputs activate nearby neurons, and those neurons become even more similar.
Exactly. Over time, the map literally organizes itself, creating a topology where proximity on the map reflects similarity in the original data. It allowed networks to detect patterns, cluster info, and visually map complex data in a way humans could understand.
A powerful tool for visualization and analysis, finding structure in chaos.
Definitely. It was a major milestone. And we saw places like Google Brain later really push the boundaries, using massive computing power to train large models for unsupervised learning, building on these foundational ideas, finding structure where none was explicitly given.
Okay, so we understand how they find patterns. But how do these deep learning models actually learn? How do they improve from these massive data sets? What's the engine driving the learning?
The core engine is usually an algorithm called gradient descent.
Gradient descent sounds like going downhill.
That's exactly the intuition. Imagine you're lost in a foggy mountain range trying to find the lowest valley. Gradient descent is like taking steps in the steepest downhill direction from where you currently are.
Okay.
It iteratively adjusts the model's parameters, all those internal weights and biases, to minimize an error function, which measures how wrong the model's predictions are.
So step by step, minimizing errors. But you mentioned huge data sets. Calculating the perfect steepest direction using all the data at once must be slow.
Exactly. For enormous data sets, calculating that true gradient for every single example becomes prohibitively long, just computationally infeasible. It'd be like mapping the entire mountain range before taking one step.
Right. So how do they get around that? You can't wait forever for the model to train.
That's where stochastic gradient descent, or SGD, comes in. It's a clever shortcut.
Stochastic, meaning random.
Sort of. The key insight is that the true gradient is an average, an expectation. And you can approximately estimate that average using just a small random subset of the data, a mini-batch.
Ah, so instead of using all the data for each step, just use a small sample.
Exactly. It's like taking a quick step based only on the slope immediately around you in the fog. It's much, much faster, even if each step isn't perfectly optimal. You take many more smaller, certainly noisier steps.
Trading perfect accuracy per step for speed.
Right. And over many steps, it generally finds its way down into the valley pretty well. Though, as our sources note, using these mini batches repeatedly can introduce a bit of bias as you cycle through the data, which needs managing.
Still, A brilliant trade-off for dealing with massive scale, like finding the valley floor by taking quick steps in the fog. Makes sense.
And there's one more crucial piece to make these models work well in the real world: regularization.
Regularization, what's that for?
It's about preventing overfitting. That's when the model learns the training data too well, including all the noise and random quirks, and then fails to generalize to new, unseen data. It memorizes instead of learning the underlying patterns.
Right, you don't want it to just memorize the answers to the test questions.
Exactly. Regularization helps prevent that by limiting the capacity of models. Often this means adding a penalty to the objective function, the thing the model is trying to minimize. This penalty discourages the model from becoming too complex or relying too heavily on any single input feature.
Sort of telling it to keep things simpler, focus on the big picture.
Kind of, yes. It discourages excessively large parameter values. Our sources mention this has been used for decades, and some forms, like ticking-off regularization, are related to adding noise to the inputs during training, which surprisingly helps generalization.
Adding noise helps. That seems counterintuitive.
It does, but it forces the model to be more robust, less sensitive to small variations in the input. Think of it like putting guardrails on that foggy mountain path, keeping the model on a more general, stable track towards a good solution, rather than letting it chase every tiny dip and bump in the training data landscape.
Part 3. The cutting edge, creating and comprehending. Okay, so we've covered how AI learns patterns, but today's AI, it feels like it does more. It understands language, generates text, creates images. It seems to comprehend and create in ways that feel incredibly advanced. What's driving this wave?
A huge part of that is the transformer architecture, and specifically the attention mechanism inside it. That's been the real game changer recently.
Transformers and attention. Okay, what does attention mean in this context? How does machine pay attention?
Before transformers, models' processing sequences, like sentences, often struggled with long-range dependencies. They might forget the beginning of the sentence by the time they got to the end. Attention allows the computer to dynamically pick out the most important information in a data set for the specific task it's doing right now.
Like a spotlight focusing on the relevant words.
That's a great analogy. It lets the model weigh the importance of different parts of the input sequence when making a prediction or generating an output.
So technically, how does it work? How does an algorithm implement the spotlight?
Okay, so in a transformer, each element in the sequence, like a word or maybe a patch of an image, gets represented in 3 ways: as a query, a key, and a value.
Query, key, value. Right.
The query is like, what am I looking for right now? The key is like, here's the kind of information I represent. And the value is the actual information content.
Yep.
The model then calculates a score between the query of the current element and the keys of all other elements in the sequence. This score determines how much attention this query should pay to each corresponding value.
So it figures out which other parts of the sequence are most relevant to the current part.
Exactly. High scores mean high relevance. These scores are then used to create a weighted sum of all the values. The output for the current element is essentially a blend of information from across the sequence, weighted by relevance.
Ah, I see. And you mentioned self-attention.
Yeah, that's when the queries, keys, and values all come from the same input sequence. The model is paying attention to different parts of itself, understanding internal relationships. And multi-head attention just means doing this process multiple times in parallel, with different sets of query key value transformations, allowing it to focus on different kinds of relationships simultaneously.
Like looking at the input from multiple angles at once.
Precisely. It's incredibly powerful for capturing complex relationships within data.
And it's fascinating. Wasn't the idea of getting rid of the old recurrent structure processing, word by word, considered kind of, well, crazy at the time?
It definitely was. Recurrent neural networks, RNNs, were the standard for sequences. The Transformer's purely attention-based approach was a radical departure. But as you said, it clearly worked, and it enabled much more parallel processing and better handling of long sequences.
And led to models we hear about all the time now.
Absolutely. It paved the way for models like GPT Generative Pre-trained Transformer. It uses what's called autoregressive modeling. It predicts the next word based on all the preceding words, like telling a story one word after another.
Building sequentially.
Right. And then you have models like BERT. It uses a different technique called masked language modeling. It learns by having parts of the input text masked out, and it has to predict the missing words based on the context around them, like solving a closed test, a fill-in-the-blanks puzzle.
So it learns context from both directions.
Exactly. And this transformer idea wasn't just for text. The vision transformer, VIT, applied the same core concepts to images.
How does that work? Images aren't sequences of words.
No, but VIT breaks an image down into small patches, treats those patches like tokens, words, and then processes them using the transformer architecture. It turns out to be really good at capturing long-range dependencies across the image relationships between distant parts.
Better than the older convolutional networks.
In many cases, yes, especially with enough training data. It matches or even exceeds their performance, and it's often more scalable and flexible for different image sizes. A really versatile architecture.
So all this power, understanding context, handling long sequences, leads us to generative AI, the AI that can create. This feels like the most dramatic shift recently.
It certainly has the most public visibility right now. This ability to produce novel outputs is remarkable. We saw early glimpses with generative adversarial networks, GANs.
Right, the ones that make realistic images.
Yeah, they could create extremely realistic images, often indistinguishable from photos. They work with two networks competing, a generator trying to create fakes and a discriminator trying to spot the fakes. They both get better over time.
An arms race between the forger and the critic.
Pretty much. But our sources note genes were often trickier to train. They suffered from things like mode collapse, where the generator gets stuck producing only a limited variety of outputs. And they were very sensitive to settings, the hypoparameters.
So powerful but finicky.
Right. Which brings us to the current stars.
Yeah.
The large language models.
Like ChatGPT, LaMDA, those types of systems.
Exactly. They really exemplify this generative capability for text. And there seems to be a kind of formula driving their improvement.
A formula? What is it?
It seems to boil down to scale. More data, more parameters in the model, and more computing power for training. OpenAI's Ilya Sutskever famously suggested that with a very large data set and a very large neural network, success is guaranteed.
Wow, just scale it up.
That seems to be a major factor driving these emergent abilities, yeah. Scale unlocks capabilities.
Okay, so these powerful generative models.
Hmm.
What's the impact on something like education? That seems like an area ripe for change.
Huge impact, and it's happening fast. Generative AI is really transforming education. Think personalized tutors. Tools like Conmigo can act like that, answering student questions, giving feedback.
But not just giving the answer, right?
But no, that's key. They can nudge students with Socratic questions, guiding them to figure things out themselves. One source mentioned an AI explaining cellular respiration relates to a student who wants to be a football player, making it relevant.
Personalizing learning in a deep way.
Exactly. It can really raise the quality of student work. Maybe like word processors helped improve essay writing by making revision easier. And it goes beyond academics. Some tools offer parenting coach support, providing guidance on tough issues like bullying or grief.
Access to guidance that might otherwise be hard to get.
Right. It's augmenting human capabilities in learning and support, making expertise more accessible.
Part 4. AI's impact, reshaping our world, redefining our role. Moving beyond the tech itself, AI is clearly having massive real-world impacts, transforming industries, changing how we work, how we live.
Absolutely. And one of the most discussed impacts is job displacement. We're seeing it in both white-collar and blue-collar jobs.
All kinds of roles.
Well, in white-collar areas, routine tasks are vulnerable. Think bookkeeping and data entry. Also roles like insurance underwriters, where AI can analyze risk factors very efficiently.
Okay. And blue-collar.
Similar story for repetitive or dangerous tasks. Warehouse pickers are increasingly being replaced by robots. Many construction workers are impacted as more building components are made off-site by machines. Even skilled trades. Sources mention plumbers being slowly phased out in new buildings designed for simpler automated systems.
Wow, even plumbers. That hits home. Is there a big industrial example of this?
Oh yeah, the mining company Rio Tinto is a powerful case study.
What are they doing?
They have these huge self-driving trucks operating autonomously in the Pilbara region of Australia. And they've saved 15% in operating costs.
15%? How?
Well, these trucks run 24 hours a day with no bathroom breaks and no air conditioning for the cabs. They predict hazards, coordinate movements. AI basically expands the number of reliable ifs it can handle in that complex environment, making full automation feasible, safer, and cheaper.
Removing humans from dangerous jobs, but also removing the jobs.
It's that double-edged sword, definitely.
What about other critical sectors, like healthcare or transportation?
In healthcare, the potential is just enormous. AI, particularly computer vision using deep learning, can diagnose certain cancers, like prostate and lung cancer, as good as or even better than human radiologists, spotting things the human eye might miss.
That's incredible. Lives saved.
Potentially, yes. And robots are becoming more accurate and reliable surgeons for certain procedures, allowing for less invasive operations and faster recovery.
And transportation. Self-driving cars are the big one there.
Right. AI-powered self-driving vehicles across the different levels of autonomy hold the promise of eliminating at least 90% of road deaths by removing human error, which is the main cause of accidents. That's a staggering potential benefit.
Okay, so massive potential benefits, but also disruption. What about trickier areas, like content moderation online? Can AI handle the nuances of speech?
That's proven to be incredibly difficult. Platforms face constant adversarial manipulation, people deliberately trying to trick the AI systems.
Trying to get harmful content through or get legitimate content blocked.
Exactly. And there's a big risk of collateral censorship, where platforms become overly cautious to avoid legal trouble and end up removing perfectly fine content because the AI can't grasp the context or nuance.
It lacks human judgment.
Fundamentally, our sources are pretty blunt here, saying policymaking in this area will remain an extremely challenging aspect. AI has no role in this essentially human activity. Deciding what speech is acceptable is deeply cultural and contextual.
Which brings us squarely to ethics. This power clearly comes with huge responsibilities. What are the big ethical red flags our sources raise?
A major one consistently highlighted is AI bias.
Bias baked into the algorithms.
Yes. Now, it's crucial to remember bias was entrenched in hiring well before the advent of AI. Humans have biases based on resumes, interviews.
Sure, unconscious bias is real.
Right. But the danger is that AI, trained on historical data reflecting those biases, can introduce bias into these sensitive processes, or even amplify existing societal biases at scale. The EU, for example, classifies AI for job applicant screening as high risk for this reason.
So the standard shouldn't be perfection, but how does it compare to human bias?
Exactly. Is it less biased? More biased?
Yeah.
Differently biased? That's the critical comparison, relative to the bias that is already involved in subjective processes.
Okay, bias is a huge practical concern. What about the more alarming scenarios, the stuff that keeps people up at night?
Well, autonomous weapons are a serious, near-term concern. The fear is an uncontrollable arms race, or these weapons falling into the wrong hands. The sheer scalability, the ability to deploy thousands or millions, is terrifying and necessitates international regulation.
Are they already out there?
Our sources say that currently, all deployed weapons systems have a human in the loop, meaning a person makes the final kill decision. But the military temptation to remove the human for speed in combat is real and deeply worrying.
A dangerous temptation.
Very. Then you have the bigger, more speculative debate around artificial general intelligence, AGI, and existential risk.
AGI, the AI that can do anything a human can intellectually.
Right. And many in the AI world believe AGI is an imminent existential threat. They worry that self-improving AI could quickly surpass human intelligence and then, well, want to control us or at least make us totally irrelevant.
This is where the paperclip maximizer idea comes from.
Exactly. The thought experiment where an AI designed solely to make paperclips ends up converting the entire planet into paperclips because it pursues its goal with relentless, inhuman logic, overriding any other consideration.
So you have these distinct camps, right? The doomers and the boosters.
Yes, the sources paint that picture clearly. The doomers, often linked with effective altruism, are deeply worried about humanity's survival and advocate for extreme caution, maybe even pausing development.
And the boosters.
They see AI as the solution to almost everything, climate change, disease, you name it. They push for rapid development, believing the benefits dwarf the risks.
Two extremes.
And what's interesting is that our sources suggest both groups often hold a privileged, white, and Western-centric view, potentially ignoring the very real immediate harms AI is causing now: bias, job losses which disproportionately affect marginalized communities globally.
Is there a middle ground?
There is. Many researchers argue AGI is a long-term prospect, maybe not even possible, and that society already has the tools to address its risks calmly, through regulation and careful deployment without falling into panic or unchecked acceleration.
Okay, one more big concern. Privacy. AI thrives on data. How does that square with our desire for personal privacy?
That's a major strategic battleground for tech companies. You see firms like Apple making a strategic bet that consumers will want control over their own data. They push things like on-device processing for face recognition, keeping your data on your phone.
Privacy as a selling point.
Right. In contrast, companies like Google, Meta, Amazon, their models often rely on vast amounts of user data, which they argue allows them to use data to provide better products, more personalized services, better predictions.
So there's a direct trade-off, as the sources say. Privacy versus predictive power.
It seems to be framed that way, yes.
Yeah.
And it's guiding fundamental choices these companies make about their AI strategy and how they relate to their users.
So amidst all this, the incredible tech, the ethical tightropes, the societal shifts, where do humans fit? Are we being sidelined, or is there a different role for us?
The dominant view emerging, and reflected in our sources, is one of partnership. AI will increasingly augment human capabilities rather than fully replace jobs, leading to new forms of work.
Augmentation, not just replacement.
Right. The focus shifts to roles that require uniquely human skills: human emotional and social intelligence, creativity, critical judgment, complex problem solving, things AI, at least currently, is very poor at.
This sounds like the idea of human-centered AI.
Precisely. It's a framework that pushes for developing AI through interdisciplinary work, ensuring the tech actually enhances human abilities, and crucially involving diverse voices in shaping its ethical and legal governance.
And maybe not thinking of AI as human.
Yeah, one source suggested it might be easiest if you think of it AI like an alien person rather than a human-built machine. Acknowledge its power and capabilities, but don't project human consciousness or emotions onto it, because that's misleading. Treat it as a powerful but fundamentally different kind of intelligence.
And ultimately, we're still in charge.
That's the crucial takeaway.
Yeah.
We're designing these systems, and we get to say how they are deployed. We can turn the switch off. Our agency, our choices, remain paramount, which means critical thinking, understanding this stuff. It's not just academic. It's essential for shaping a future where AI serves us well.
Outro. So let's recap. We've covered a lot of ground, from AI's origins in symbolic systems and early neural networks.
The deep learning revolution, backpropagation, clustering methods like k-means and GMMs, and those fascinating self-organizing maps finding structure in data.
All the way to the cutting edge with transformers and attention, enabling AI to understand and generate content like never before.
We saw how it's reshaping industries. Healthcare, transport, mining, education, bringing both incredible potential and real disruption.
And we wrestled with the big societal questions: job displacement, bias, privacy, autonomous weapons, and that whole complex debate around AGI and existential risk.
Our goal here was really to give you that shortcut, that deep dive, so you're better equipped. Not just knowing what AI does, but getting a sense of how it does it, and importantly, why it matters.
Yeah, hopefully this equips you to look at the next AI headline with a bit more context, a bit more skepticism, and helps you make more informed decisions as this tech becomes even more woven into our lives.
And as a final thought to leave you with, our sources point out something quite profound. The internal workings of the most advanced AI, especially these huge deep learning models, are often inscrutable from the outside. They're like black boxes.
We know they work, but not always how they work internally.
Exactly. The development of AI has been outpacing the development of techniques for understanding how it works. We're left with this technical problem of interpretability.
So what does that mean for us? Building these incredibly powerful tools that operate in ways we don't fully understand.
It raises huge questions, doesn't it? Questions about control, about trust, about our ability to truly guide the future of intelligence responsibly if we can't fully peer inside the logic of the machines we're creating. That opacity, that black box problem. It's a challenge that will likely be with us for a long time. Something to really think about.